of a floor function, I'd like to remind you a little bit just about what the floor function means. Like, for example, if we take the floor of, let's say, 5.6, and y'all, this is sometimes called the greatest integer function or the integer part. Now, the integer part of this argument here, 5.6, is certainly equal to 5. Okay, certainly equal to 5. So the floor function always returns an integer. You know, for example, just simple example here, the floor of 4, the floor of any integer is just the integer. 4 is an example here. Okay. Now, so what we're asked to do in this particular problem is take the limit of a floor function as x approaches 3. Now this work right here, I just completed the squares you guys noticed. And this, I know a lot of you recognize this as just a parabola that opens down. Now the vertex v, we'll call v vertex, is clearly equal to 3, 9. Okay. This function achieves a maximum value of 9 at the x-coordinate 3. Okay, so v stands for vertex, folks. And again, this is a very familiar procedure to complete the square to determine that vertex. All right, so that helps us along quite a bit right here, because just by knowing what the graph looks like, you can make these two statements right here. Okay, again, when you put 3 into this expression, you would get 9. But until you, numbers to the left of 3 are going to have a floor of 8. In other words, starting at 2 all the way up to 3, the floor is clearly going to be 8 in this interval. Okay, and similarly, in the interval from 3 to 4, the floor is going to be also 8. Now, I'll just get a picture of that drawing here. Let's see if I can switch markers, you guys here. Okay, let's see here. Am I going to have any luck with that? Okay, there we go. Now, y'all, so this red expression over here is what we call the left-hand limit. The superscript minus means approach from the left. The superscript plus means approach from the right. And so, in other words, the graph of the floor function really is just this underlined red piece right here. Now, I'm going to leave an intentional gap right there. And so that would handle this part of the limit right here, right? The value of the floor function is 8 anywhere in this interval from 2 until 3, all right? Now, when you actually get to 3, you're taking the floor of 9, because if you put 3 right here, you get 18. 18 minus 3 squared is 9. And so remember, the floor of a constant is that constant. So this red graph that you see right here is literally, you know, I'm making that a little exaggerated right there, but you see there's a gap right there. Okay, and so again, this is a picture of the floor function. And so the answer to the question is this right here, 8. Okay, just using graphical information. Now, if it wasn't so easy to draw the graph, it would have to be quite a bit more numerical. But the answer to the question is 8. The limit of the function is 8, even though the parent function itself actually peaks out at 9. Okay, now, and again, if that doesn't make much sense to you, just think of a number in this interval, like, for example, 2.6 might be right here. So you would have the floor of 2.6. Excuse me, yeah, the floor, no, let's say, I'm sorry, let me pick another number. Let's say 8.7 or something. So the floor of 8.7 would be somewhere in that interval. I'm making that up, folks. It's just a number in that interval somewhere. Okay, maybe about right along in here. Okay, so the floor of 8.7 definitely is equal to 8, all right? Just like any other number in that interval is going to have a floor of 8. And so that's why we draw this horizontal line, y equals 8, gap, y equals 8, right there. Okay, now another interesting thing about this is an example of a function whose limit exists, but the floor function itself is discontinuous. This is what they call a removable discontinuity. If you want to take a look, this isn't exactly what I meant to talk about. But this is a nice example of a removable discontinuity. In other words, we could redefine the function at 3 to be 8. Just redefine it as 8. arbitrarily, kind of in a piecewise fashion, and that we would remove the discontinuity. So that's why they call this a removable discontinuity. It's kind of a strange language, but it means you can fix the discontinuity relatively easily vis-a-vis, say, a jump discontinuity or something like that. Okay, so anyway, folks, but this is the final answer. The circled result here, x equals 8, is the final result. And so anyway, let me know what you thought. Hope you enjoyed that one.